Hello everybody. Now we'll move on to lecture 4b, which is about the cable equation and Rall's law. And just to recap, we're discussing cable theory, which is the physical basis of brain computation. It tells us how signals propagate in neurons, and it tells us how to do the mapping between cell morphology, its shape, and its electrical properties. And we'll be seeing a lot more of this latter point today. Okay, just to remind you about the morphology of cells, here's this slide from Ramon y Cajal, which I've already shown you, showing you some of the examples of the many cells, the beautiful butterflies that he drew with all their diverse morphologies. And we are going to be looking at a lot of this gentleman's work today, Wilfred Rall's work. And just to remind you, his contribution was to emphasize that the geometry, the structure of neurons plays a huge role in their function, that neurons with their lovely branches are not simply point or spherical objects. Okay, some more reminders. We are doing everything in terms of equivalent circuits because this is the biophysical mapping of the electrical properties of a passive piece of cable. The axial resistance along the length of it, the membrane capacitance across it, the membrane resistance again across the membrane, and the membrane potential, and the outside being ground, and the inside over there being the internal membrane potential. We've seen the theory, the concept here of signal propagation along a cable, and we've seen a simulation which describes how signals decay with distance when you have a current step, and you've also seen how signals decay and change amplitude and become broader when you have a current pulse. So we've seen all of these things in the past class and example demos. So now let's get back to this business of subdividing a cable. How do you go from this kind of a blocky, chunky set of compartments, which admittedly do behave in some of the correct ways, that is, the signal propagates, it gets smaller and so on. How do you go from here to cable theory, which is a precise statement of the mathematical function of how signals propagate? And I'm not going to go through the details of the derivation. It's actually not a difficult derivation. You're welcome to look it up. But I'm just going to give you a flavor of how it's done. So the blocky idea, the coarse-grained idea, is that you say that here's a compartment, here's a compartment, here's a compartment. That's all very well. You've done all the calculations based on this. Now the trouble is, of course, these compartments are not small objects, right? They're fairly long as drawn over here, and therefore there's an approximation taking place, and we've already had the discussion on it. The approximation being that we treat the internals of the compartment all as uniform at uniform potential, but we treat all of the resistance, the RA terms, as being localized at the junctions. Now that's not quite right. Yeah, what's actually of course the case is that the membrane resistance is a continuous property. Okay, so how do you approximate it? So now think back to your high school days when you were just beginning calculus and you kept hearing this thing, right? That the way you handle something which varies continuously is you approach it by making the subdivision smaller and smaller, and in the limit, as it tends to zero, it will it'll give you the same mathematical properties as you would get from the truly smooth distribution. And that's what you do. You take these compartments and you subdivide them. You make very thin salami slices, and you make them smaller and smaller. You make them tend to zero, and in that limit, your approximation of placing the potential within a compartment is uniform. That approximation becomes arbitrarily good, right? And so you can treat your series of very small compartments almost exactly, and in the limit exactly, like a biological cable. So that's the general approach that one takes. One basically takes our standard little equivalent circuits describing the compartments, and one makes more and more of them, but smaller ones, so they're describing the same overall length. And in the limit, this approaches the exact behavior if you had an ideal cable. Okay, so that is the general idea behind cable theory. And once you've gone through it, turned the handle, done a little bit of calculus, you end up with this equation. Yeah, these are actually the same equation, it's just rearranged a little bit. And what it tells you is that the second partial derivative of the membrane potential V as a function of distance along the length of cable, yeah, dou squared V by dou x squared, is equal to the unit length axial resistance, small r A, times the stuff in this bracket. And the stuff in this bracket is what? It is the membrane potential minus the resting potential divided by the membrane resistance. Note that this is V divided by R, so you have a current term here. And you have here, you have a capacitance times a rate of change of potential, which is of course also a current term. So all of this is a current term, and you're multiplying it by R, and current times R is a voltage term, and hence you have this voltage dependence over there. So that describes voltage as a function of position and also as a function of time, and this is the cable equation. This is the same thing, it's just rearranged a little bit, yeah. So Rm by Ra into the double derivative with position is equal to V, and we've gotten rid of the E leak term since it's a constant, just for the purposes of calculation. It's equal to V plus Rm Cm into dV by dt. So this form actually is kind of nice, because what it does is it takes out two constants, which we're going to run into quite a lot, and these are very important. So this is a constant of, you can see that it's multiplying the rate of change with respect to position. So this is a constant of position. This is a length constant, and it's called lambda. And for various algebraic reasons, partly because this is a double derivative, this is actually length constant lambda squared. So Rm by Ra, where Rm and Ra are per unit length of cable, this is equal to lambda squared. And here we have another familiar thing, which is Rm times Cm, again per unit length. And these multiplied together gives us a time course, because this is a derivative with respect to time. So here you have the length constant, and here you have the time constant. And we will be coming back to these terms in just a moment. So implication number one, right? So let's take our cable equation and say that we are going to ignore space. So if, in other words, we're treating it as a single point, a single compartment. Well, if you do that, what happens? You don't have space anymore, so the derivative with respect to space vanishes. It becomes 0. So this whole equation, this term vanishes, becomes 0, and then you get just this bit left. And this bit basically relates derivative with respect to time to some other value. And those of you who've done this kind of thing in school and college know that this kind of equation, where you have a rate of change with respect to time and voltage on the other side of the equation, you end up with an exponential decay term. And lo and behold, what we have here is our old friend Rm and Cm multiplied by each other, which is a time course. And so what you end up with is the membrane potential at any given time is the original membrane potential times this exponential factor of minus time over time constant. And then that Em over there is just to make sure that you have the right overall potential. So Rm/Cm is equal to tau, which is the time constant. Yeah. So here you have a simple exponential decay if you ignore the space. That's one result. Here's the equivalent result if you now ignore the time. Yeah, so dV by dt has become 0. So this part of the equation has vanished. And so now you have d squared V by dx squared is equal to this part of the equation, this part having vanished. And it turns out that if you solve this, you get a solution of this form: E leak plus some constant into x by lambda minus this into x by minus x by lambda. And lambda is the space constant, which is equal to this term in unit lengths, Rm by Ra. And if you want to convert it into your more familiar units, it's equal to the specific membrane resistance times the diameter divided by 4 times this axial resistivity in regular units. Okay, and square root of the whole. So this is the space constant. So this tells you how it declines with distance. And so here we have it. Yeah. So just some nomenclature so that we're all on the same page. The length of a dendrite or axon is just the length. It's a distance. It's in microns or meters or whatever your unit of length is. Lambda is a length constant. Its units are also length, microns, meters, whatever you choose. Capital L, which is something very, very useful, we'll come back to it a lot, is the electrotonic length. It is the number of length constants in the cell. So in other words, it is the total length of the cell divided by the length constant, and this tells you how many length constants are present in the overall length of the cell. Just so that you know, the typical length constants of a large cell are typically 2, so that the length is roughly twice lambda. And again, just that you have a general sense of it, the length constant lambda in microns is of the order of 2 to 500 microns. So it's quite a long distance. In fact, as large as many cells. Okay, so just to recap, here is what cable theory tells us. If you have a point cable, in other words, just a single compartment, a small spherical cell, then you have no dependence on distance, and your potential decays as a function of time like an exponential with a characteristic time tau. If, on the other hand, you don't worry about time, you let time proceed until infinity, and you have a certain potential at the beginning of your cable, and the cable is infinitely long, then the shape of the decline of potential along position is now also an exponential, and in this case the length constant is lambda. Okay, so nice and symmetric in time and space. In both cases it is an exponential decline as you increase the variable, in this case time, and in this case position. Okay, so that is what cable theory tells us will happen as a signal propagates along a cable, and we've already seen some of this through the simulation. Let's now move on to something which Wilfred Rall came up with, which is actually one of the very nice simplifying insights. It's not a perfect approximation, but it's a lovely simplifying insight that he came up with. And what he asked was, what happens when you have a branching cell? So just so that you are able to bring your concepts over, what happens when you have a branching cell in terms of equivalent circuits? So let's suppose here is our equivalent circuit of the compartment right there, yeah, just before the branch point, so this compartment here. So it's a standard equivalent circuit, and now you want to branch it into 2 little compartments, yeah, the purple one and the red one. And all you have to do is you just have to have 2 little compartments in parallel, right? So the inside of the cell, which is the top part over here, it goes to the axial resistance, and it branches into the purple compartment, which is just a regular compartment, and it also connects up to this one, and so here you have another equivalent circuit. Please remember that the outside of the cell, all of these compartments share the same ground, and as you can see, the same ground wire is present throughout, but the inside is connected via the axial resistances. So all you have to do to get branching in an equivalent circuit is to connect up the compartments inside to inside and outside to outside, and now you have a branching cell. Okay, so this is the equivalent circuit manifestation of this. Now let's see what Rall came up with. So what Rall did, to understand it, let's just spend a couple of moments defining some things or reminding you of some things. Yeah. So just to remind you, the electrotonic length L is equal to the actual geometrical length divided by lambda divided by the length constant. So that's just a reminder. And we're going to say that your electrotonic length over here is something called L0, and your electrotonic length over here is something called L1. So these are different values of electrotonic length for different parts of the cell. What Wilfred Rall said was that if you have a cell which is branching, and the parent branch has an electrotonic length constant L0, and it has 2 branches with electrotonic length L1 and L1, both are L1. Each of these having diameters D0 for this compartment, D1 for this compartment, and D2 for this compartment. They don't have to be identical. Electrotonic length has to be identical. He showed mathematically that this branching structure is equivalent to a single cable of total electrotonic length L0 plus L1 and of diameter D0, right? So that's actually quite a remarkable simplification. It says that even this branching structure can be treated electrically speaking. Of course, it's not identical in terms of morphology. It's not identical in terms of where the synapses are connecting. But electrically speaking, and we'll see what the limitations are, electrically speaking, this is equivalent to a single cylindrical compartment of diameter d0, electrotonic length L0 plus L1. So we'll see exactly what this means in a bit. So, but first, what are the conditions? What has to be satisfied for Rall's law to hold? There are 4 conditions. First of all, it assumes that the cell properties, the passive properties Rm and Ra are uniform. Yeah? You can't have a different membrane here from there, and that's not really likely anyway. Yeah? So this is generally easily satisfied. There are cases where the membrane properties differ, but they're very, very unusual. Second, you have to have the same ends. Now, this is a somewhat subtle point. It comes out from boundary conditions in differential equations. We won't go into that. But basically what it says is that if you have a sealed end over here, in other words, if you don't have any holes in the cell at this end, you shouldn't have any holes in the cell at this end. So again, that's not a very difficult condition to satisfy. You don't have open ends at one part and closed end at one part. Basically, if you have an open end in a cell, it's a dead cell. So this condition 2 is readily satisfied. Condition 3 is, as I said, that the electrotonic lengths of the 2 branches should be the same, L1 and L1. That we'll come to in a bit. And finally, this is perhaps the crux point of it, which is telling us what is the relationship between the diameters. The parent diameter to the power of 3 by 2 should be equal to the sum of this diameter d1 to the power of 3 by 2 plus d2 to the power of 3 by 2. So this is a little bit like Pythagoras' theorem, but here the exponent is 3 by 2. Okay, so this is the 4th condition, and this is the crucial one. d0 3 by 2 is equal to d1 to the 3 by 2 plus d2 to the power of 3 by 2. Okay, so keep it in mind that if these conditions are satisfied, then you can treat this whole thing just like, as we saw a moment ago, like a single cylinder. Okay, so this is the implication, though. This is a very interesting implication. What it says is that even if you have a really complicated branch structure in a cell, provided those conditions are met, then you can treat the whole thing as one big equivalent cylinder. And the reason why this works is as follows. Here you have your parent dendrite, and it has branched into 2 little branches. We're going to ignore the spines for now. Yeah, it's branched into 2 little branches, and you can sort of understand that if you were to cut the cell off until here, it would obey Rall's law. What now do you do about the next branches? Well, you can do a clever trick. You can say that, oh, okay, here's my parent branch, and I'm going to branch it into 2 little branches, and provided this thing obeys Rall's law, then we could treat this thing up to there as part of the same equivalent cylinder. But we can go to the next level as well. Yeah, we can say that this parent branch, if it has these 2 little branches which obey Rall's law, then this thing is a single branch. And similarly, these 2 things with that as a parent branch can be made an equivalent cylinder. And then you do this what's called recursively. You do it again, and now you said, okay, now we made these 2 things as an equivalent cylinder, as an equivalent to 1 branch. So now you can collapse these 2 into that, and now you do the whole thing for the rest of the cell. You said, okay, well, now this whole thing can be treated as each of these can be treated as a single one, and now you collapse all of those into this, and so you end up with 1 single cylinder that represents the entire cell. Remarkable. So you should ask, and you must ask, in fact, how well are these conditions met? And it turns out that the conditions are actually reasonably well met, good enough for many practical purposes for many kinds of neurons. Specifically, it is reasonably well met for many pyramidal neurons, which are one of the major excitatory neuron classes in the brain. So this is true, this is almost always true, this is reasonably well met, and this is reasonably well met. So it turns out that Rall's law suggests that you can take most of the major cell class in the brain and treat this complicated branch as just 1 single equivalent cylinder. Isn't that neat? There is one more subtle caveat which I need to emphasize to you. and it is that Rall's law is asymmetric. It depends where you are recording from. If you're recording from the cell body, then this is your D0, these are your D1s, D2, and so on, right? And so then you can, and of course they're getting smaller as you go along, and so then Rall's law is correct. It works if you're recording from here. But what happens if you were recording from there? This becomes your D0, but that is almost as big as D0, and that's even bigger than that. So the Pythagoras theorem, like d to the power of 3 by 2, fails if you are recording at the small end of the neuron. In other words, Rall's law works as seen from the soma. It does not work as seen from the tip of the dendrites. Okay, so that's one caveat that you have to keep in mind with Rall's law. Now, it turns out that practically always when you record from a neuron, you are recording from the cell body, so you're in luck. You can usually apply Rall's law. Okay, so now I'm going to change gears a little bit, right? So we've used Rall's wonderful law to make this very, very simple. Now what we're going to do is we're going to use another of Rall's theorems, not the same as the branching one, a different one. And this one will help us figure out how much you can learn about a neuron just by recording from one electrode. You stick an electrode into the cell body, and the simplest thing you do is apply a current pulse. Note that this is happening without any active channels. So in real cells, you would start to get action potentials here. Here we're just ignoring the active channels. You can do that if you put in blockers for all the ion channels, and you get a nice passive response. What can you learn from this? Whenever you have these kinds of questions, you should go back and think about your equivalent circuit, and that's what we will do. We apply a current pulse I, and we measure the voltage. And what we're doing in terms of equivalent circuit, we are applying a certain current pulse down here. Now, let's start out. What is EM? What is the resting membrane potential? Yeah, this is something we want to know. How do you get it? Well, this is actually very easy to get. You apply zero current over here. That means that the potential across this resistor is 0, right? This is the electrode resistor. The potential across this is 0 because there's no current flowing through it. You're just measuring the resting potential without applying any current. And when you do that, there's no current flowing there, there's no current flowing there, there's no current flowing there, and you end up just measuring EM. So that's one thing you can get right away. You just stick an electrode into a cell, you don't pass any current, you just measure the potential, and you will end up measuring the resting membrane potential, not surprisingly. That's why it's called the resting potential. Okay, so good. You've gotten one electrical property out of the various electrical properties that you have in this equivalent circuit. What else can you do? Well, think about it. You have applied a certain current pulse, and you've measured a certain voltage deflection. Maybe you can do something with that. And indeed, you can do just that, right? If you wait until the pulse has settled, you're in this nice position now where the only current going is not going through the capacitor anymore because this is fully charged. The only current is going down this way. We're going to ignore the axial resistance for now. Yeah. So now you have a certain current going. It goes through here, it goes through here, it goes through here, and it goes and it bumps into the membrane potential, and then it goes to ground. So now how do you eliminate the resistance of the electrode? Well, that's actually very easy to do. Even before you hit the cell, you just measure the resistance of this by passing a current through it when the other end is in solution, when the other end is at ground, and then you can measure our electrode. So you can ignore our electrode. Now you're in a position to measure what is the input resistance of the cell. You apply a certain current. This current goes through the electrode and it goes through the membrane resistance. Together those are summed up to give you our input. Yeah? Our electrode plus Rm gives you our input. We already know our electrode. You get your total membrane potential V when the current I is passing through the electrode and the cell. That V is equal to the input resistance times the current plus the membrane potential. And so by eliminating these terms, you get our input, and then you can eliminate that term and you end up with Rm. So you can measure Rm also from cable theory. That's useful. Okay, now what else can you get from this electrode? Well, you will remember that when you apply a current pulse, there is a certain charging time course, and this has a certain relationship to the membrane properties. In fact, the charging time course is tau, yeah, if you remember your cable theory. So tau, what does tau relate to? Well, tau turns out to relate to Rm times Cm, right? So here's that charging curve. In this case, a discharging curve. A charging curve would be like this. And if you measure the tau, the time course of this charging curve, so that time is tau, and that is simply equal to membrane resistance times membrane capacitance. Very straightforward. You've already measured membrane resistance. So now, given that you know tau, given that you know Rm, you can estimate Cm. You can measure the capacitance of the cell as well. Okay, so this is very handy. And remember, you've done it all with just, so far, just with this one stimulus, this one little current pulse. That's kind of neat. Can you do anything even further than this? And this is where Wilfried Rall told us that you can do one more piece of information. And it's kind of nice because it kind of finishes up the kinds of parameters you would like to know. What he showed was that because of Rall's law, if you can treat the cell as one long cable with a total electrotonic length of L, yeah, it turns out he derived an expression for L in terms of the charging time courses of the actual cell. Now, just to remind you, a perfect exponential charging or discharging time course, which is in black, a perfect exponential curve only happens if your cell is not long, if L, capital L, is very, very small, if it's just a sphere. What happens, it turns out, this is what Rall showed, is that if you have a long cell, then the charging time course is multiple exponentials added up with different weighting factors, V0, V1, and so on. It's actually an infinite series. So in red, I've sort of schematized the actual time course of charging of the cell or discharging of the cell. And what Wilfried Rall showed was that the total electrotonic length L is equal to this interesting expression pi divided by square root of tau 0 by tau 1 minus 1. And just so that you're reassured that you don't get any imaginary numbers, tau 0, the first time course, is invariably larger than tau 1, and so on. Actually, he had a more general expression than this, but this is good enough. So what does this tell you? This gives you the effective length, the electrotonic length of the cell in terms of the charging time courses. And the remarkable thing is you can do this all through this one simple experiment where you apply a current pulse. To summarize, we have done one simple experiment where we've applied a little current pulse, and we've looked very closely at the shape of the charging curve following that. And together, this gives us 4 pieces of information. It gives us the membrane potential EM, it gives us the input resistance, Rin, it gives us the input capacitance. So strictly speaking, the capacitance we measured here a few slides ago, this capacitance is of the whole cell. It's not just of the soma, because of course the other parts of the cell contribute to it as well. As a good starting approximation, we just say this is the Cm of the soma. So it gives you some measure of capacitance of the cell as a whole, which is related to the membrane capacitance, and it gives you the electrotonic length. So 4 parameters have been obtained from this very simple experiment. And this is kind of nice. This is one of the nice outcomes of Rall and his cable theory. So what can we do with all of these things? So one kind of thing which is very nice to be able to do is if you have a really, really complicated structure like this, you can make a computer model of it. And in fact, that's what we saw in the previous class. We saw a little computer model of a passive cable. And as we saw, we can reach the complicated branching structure with arbitrary accuracy by making the subdivisions smaller and smaller. It turns out that if you make your subdivisions 0.2 lambda, 0.2 times the length constant for a passive cell, that is easily good enough. That works, that gives you very good accuracy. If you make if you have an active cell, if you have lots of voltage-gated ion channels, you need to make it 10 times smaller than that. These are just rules of thumbs for how you do it. So that tells you how much you have to subdivide this complicated branching structure in order to make a good numerical cell model. And there are very good ways to do this. And you can do very large cell models very, very fast, in real time, in fact. And you'll see some simulations like that in due course. Okay, so just to recap, cable behavior is a crucial underlying property of cells which will give rise to a lot of the computations that we will see in a couple of classes. The fundamental rule of thumb, the intuition I want you to take away from all of these things is that if you apply a pulse of current at one end, you have three things that happen to the signal as it propagates down the cell. Its amplitude gets smaller, it gets smoother, and its peak gets a little bit delayed. And you can go an awfully long way with that. And you've seen some more subtle, some more quantitative aspects of cable behavior in today's class. And I will leave you with this thought of Ramon y Cajal, that is, that the branching structure matters. And now we have gotten to some insights into what these branching structures mean for electrical propagation in the neuron. So we have gone through cable theory now, all the key bits of it. We've looked at neurons and cables, equivalent circuits, Ohm's law aspects of it. We've had a little set of simulations to play with the cable equation and its implications in time and space. And now we've analyzed it somewhat more quantitatively in this class. And we've used cable theory to help us understand cell properties, and we've seen Rall's law. Okay, so here's an assignment just to make sure you keep thinking happy thoughts about cable theory and its implications. Enjoy.